Hello, this is Anthony Atkinson.
And this is Marco Riani.
Now we are going to introduce some analysis of some income data taken from our new and exciting book on robust regression analysis, which we have written with 3 co-authors.
Aldo Corbellini, Domenico Perrotta, and Valentin Todorov.
So, the data come from the United States Census Bureau. The variables, as given in the book, have acronymic names. For example, the Y, the response, is h-tot val, which is a total value of the household income. And the other ones are
the number of persons in the household, then
household other income other than regular employment, and then social security, household social value.
As usual, we start loading the data and producing a y-x plot. As expected, there is a positive relationship between the response and the 3 explanatory variables. You can also see some form of heteroscedasticity,
which may or may not be removable by power transformations of the box-Cox type.
In chapter 1, we had found the log transformation.
When the data were just treated as responses without any explanatory variables, but they are indeed actually regression data.
When we use the 3 explanatory variables, this is the Fem plot that comes out, and this is the associated procedure for finding the best value of the transformation parameter in a fully automatic way. As you can see from this plot, the best trajectory is associated with 0.5 square root transformation, and this is also signaled by the plot on the right.
Whereas for the data without regression variables, you got the log transformation, which is absolutely standard in economics for dealing with income data.
Note that here there is a grid of 0.5 in the value of the transformation parameter. Now we use a finer grid of values of lambda. So we go from 0 to 1 with a finer grid of 0.25. And then we run our automatic procedure for finding the best value of the transformation parameter, and still using this finer grid of 0.25, we end up with the square root as the best value of the transformation parameter.
Although it is clear that the values of the score statistic are influenced by some observations entering towards the end of the forward search.
And this leads to the trajectory of 0.5 falling outside the confidence bands. So we transform the data using 0.5 and we run the automatic procedure for finding the outliers in the transformed scale. These are the outliers that are found. We end up with 9 units declared as outliers. The outlying observations are clearly shown in the plot of y against x2. Now we compare the QQ plot of residuals in 3 scales.
So the first one is untransformed data for lambdas equal to 1. This is clearly nothing like normal. The second one is in the square root transformation without any exclusion of outliers. That is perhaps slightly better than no transformation, but is still outside at both ends of the plot. Whereas when we come to lambda equals 0.5 with 9 observations deleted, we get a series of points that lie almost throughout on the upper envelope. So this is more nearly normal, but is still
it is curved. It is not in the center.
Yeah, no, that's right. One still might feel a little unhappy about it.
Now we go to table 10.1, which compares the 3 feet in terms of t statistics. The original scale, we have an adjusted R-square which is a bit poor, then increases in the transform or after deletion of the outliers.
What is particularly interesting, I think, in this table is that the value of the statistic for x2 increases quite appreciably as we go from the left to right of the table, whereas the other two t statistics increase and then decrease.
Now let us analyze the significance of the explanatory variables. So we do the monitoring plot of the added variable t statistics with 99% confidence interval.
This is for, again, this is on the square root transformation.
The added value t statistic for x3 tends generally to be more and more significant. Same thing for x1. The other end for x2, as we have commented before, there is when the outlier center, there is a slight decrease in the value of the t statistic. Now we analyze the residuals in the square root scale. Well, this plot is not an event. You can find two units that have a large negative residual.
And though we don't show it by graphing, the large positive residuals are associated with the outliers, 9 outliers that we have identified.
And also probably notice that here the number of units with large positive residuals is much greater than the number of units with large negative residuals.
That's right. So this means that even though we have estimated the best transformation we can find, it hasn't actually produced symmetrical residuals, it's symmetrical distribution of residuals.
Not that these two units, 107 and 200, which at the end of research have a residual which is in agreement with that of the other units, must lie on a different side of the regression hyperplane from these units that are declared as outliers. We investigate this aspect with a 3D scatter, where we have used 3 different symbols. The 2 units that we have seen before, note that here we are on the transform scale, and then we have x1 and x2. And now we do some rotation. And you see that after this rotation, that these 2 units lie on a different side
of the fitted regression plane from the outliers, which are shown as red circles.
Right. Actually, as we have seen in the original y-x plot, there is some heteroskedasticity. Now we have a heteroskedastic regression model in the transformed scale. And these are the outliers detected using the heteroskedastic approach. The outliers that you find are again those made up of units 107 and 200, then also
the 9 outliers that we've found before, and 2 extra ones.
Now we want to pair the monitoring of the parameter estimates under the original scale and under the transformed scale. On the left you have the parameters monitoring in the original scale, so this is the heteroskedastic regression model, and you can see that in the original scale the estimates, especially of beta 2, are very unstable. On the other hand, look at the estimate of beta 2 in the transformed scale. They are much more stable. And then finally the effect of the outliers, and also the estimate of sigma square,
which is much more nearly constant in the right hand panel, which is one of the conditions one would like for some kind of robust or regression. The estimate of variance in the right hand panel looks very constant. However, This is a question to some extent of how one parameterizes one's heteroskedastic model. And we've chosen to have sigma squared times some kind of exponential function of the explanatory variables, which increases with the x's, but the sigma squared should remain constant.
Note that in both set, in these searches, we go up to n. Note that there is this decrease, for example, for beta 2 when the outliers start to enter. And in fact, we have seen that the significance of beta 2 decreases when the outliers start to enter. Once again, this is typical of the monitoring approach where you can understand the effect of a particular set of units on a particular statistic.
Our final step in this analysis was to use REVAS. This was in fact gave rather disappointing results.
Now we run the procedure for model selection with REVAS, and then we select the best model. We show the results from REVAS.
These in fact look to be quite plausible and decent fits, I think, but the value of adjusted R squared from this regression is 0.458. That is, of course, with outliers deleted.
Note that
this is appreciably worse, in fact, than the result from regression with the square root transformation when 9 outliers are detected.
So what do we conclude from the analysis of this data?
Well, one of the things we can conclude is that REVAS is a method that assumes homoskedastic errors. This is what the estimation from residuals is trying to achieve. Here, if we have heteroskedasticity, it is not surprising that REVAS does not particularly lead to an outstanding interpretation.
So in this case, there is not a big gain in going from parametric to non-parametric.
Because the non-parametric model is wrong, so it does not provide appreciable and sharp insights.
Thank you for watching, and see you to the next video.
Yes.